Good day and welcome back for part 5 of our discussion on differentiating trig functions. As indicated at the end of our previous video, there is an associated class worksheet that you can find located on Canvas dealing with differentiating trig functions. So hopefully you took the time to find the worksheet and you've spent some amount of time working through and attempting the problem. And in this video, much like I would have done if we were meeting in person, I want to go over a few of the problems on the worksheet. The remaining problems I'm going to leave up to you to continue thinking about, focus on understanding. You can compare your work versus the solutions found on Canvas, and definitely reach out to me if you have any questions. The first problem I wanted to say something about is the limit in 2b. That is the limit as x approaches 0 of x over tangent of x. Now, when it comes to new limit laws related to trig functions, recall that we have two of them. And by comparison with the formulas that we see to the right, there's only one of those that matches up, or at least looks as though it will match up with the limit of interest. And that is the first one. So somehow I want to get this to involve x and sine. So let's begin by just simply rewriting tangent in terms of sine and cosine. So this would become the limit as x approaches 0 of x divided by sine x over cosine x. And we have several options as to how we can go about manipulating this algebraically. And I will simply just multiply by 1 in a fancy way. I'm going to multiply this by 1 over x divided by 1 over x, with the goal of getting this sine x over x that we would like to see. So note in the numerator the x's cancel, and in the bottom we would have sine x over x times 1 over cosine x. And remember, dividing by a fraction like 1 over cosine x is the same thing as multiplying by its reciprocal. That is, instead of having a 1 over cosine of x appearing in the denominator, we could turn that into a single cosine x appearing in the numerator. So just kind of doing that algebraic rewrite. And note, now we are in a prime position to apply our limit laws. As long as that limit in the bottom is not 0, which it is not, we can write this as the limit of the top over the limit of the bottom. So applying our limit laws, we would have the limit as x approaches 0 of cosine divided by the limit as x approaches 0 of sine x over x. And if we evaluate each of these limits individually, note the limit in the bottom is 1, using our new limit law. And in the top, I would like to simply just substitute in x equals 0. But think for a moment, how could you justify simply just plugging in x equals 0? And the answer is because cosine is continuous, and that's the definition of continuity. So just to give a small bit of justification at this step, I'm going to go ahead and just note because cosine x is continuous at x equals 0. And when we are substituting in a scenario such as this one, we definitely should add some type of small kind of justification or side note as I've done in this case. Cosine of 0 is 1. 1 over 1 is equal to 1, which is the value of this limit. For the second problem I wanted to go over, problem 3 from the worksheet, it's one of these standard tangent line problems. Find the equation of the tangent line to the curve given by the function f of x equals 1 over sine plus cosine at x equals 0. And note immediately, without doing any work, we can write down kind of the template or the general form of that tangent line. So it would be y is equal to f prime 0, x minus 0, plus f of 0. And as usual, I'll note we need to determine two values, f of 0, the function value, and f prime of 0 from the derivative itself. So let's do a few side computations. If f of x is 1 over sine plus cosine, then f of 0 is 1 over sine of 0 plus cosine 0. And take a moment and kind of write down in your notes, what are these common trig values? What is sine of 0 equal to? What is cosine of 0 equal to? And hopefully you've written down sine of 0 is 0, cosine of 0 is 1. So f of 0 is 1 over 0 plus 1, which is simply 1. And that is the first function value we need for the equation of that tangent line. The second function value comes from differentiating f. Requires the quotient rule, and the quotient rule tells us here in words, low d high, and the derivative of that top function of 1 is 0, minus high d low. And when we differentiate the bottom function, we would have the derivative of sine, which is cosine, plus the derivative of cosine, which is minus sine. And then this is all over the bottom squared. And I'm going to go ahead and just immediately substitute in 0 and also make the observation that that first term in the numerator cancels. So when x is equal to 0, we have in the top minus the quantity cosine 0 minus sine of 0. And in the bottom we have sine of 0 plus cosine of 0 quantity squared. And remember, cosine of 0 is equal to 1, and sine of 0 is equal to 0. So what we end up with in this case is minus 1 over 1 squared, which is minus 1. And that is the second value we need it to determine to have the equation of our tangent line. Therefore, the equation of the desired tangent line will be y is equal to minus 1 times x minus 0 plus 1. And leaving it in this form is certainly okay with me. If you want to take it one quick step further and write this as minus x plus 1, that is also most definitely acceptable. This finishes up our discussion on differentiating trig functions, but as usual, this is a point where you should continue on your practice. So the graded problems make up a small subset of problems, so make sure you're looking through suggested problems and examples in the book and really focusing on understanding the material. If you have questions, drop me an email or stop by office hours. So stay tuned and take care.